SwayamPrabha. Digital India. Educated India.
I welcome you all to the session of thermal engineering basic and applied. Today we shall solve a few examples, and through this exercise we shall try to illustrate the concept that we have learned from the theoretical analysis of steam turbines. So, the first problem that we will solve today is from the impulse turbine. Let me first read out the problem statement, then we shall start solving the problem following the theoretical understanding that we have. It is given that an impulse turbine with single row wheel has mean diameter 100 centimeter and speed of rotation 3000 rpm. The nozzle angle is 20 degree and the ratio of blade velocity to steam velocity is 0.44. The ratio of relative velocity of steam at the blade outlet to that at the blade inlet is 0.86. It is given that the blade outlet angle is 3 degree less than the inlet blade angle and the mass flow rate of steam is 10 kg per second. We need to calculate a few parameters, but first we need to draw the velocity triangles, then we need to calculate the tangential, axial and resultant thrust on the blades, power developed by the blades, and lastly the blading efficiency. So, let me tell you one thing, that it is convenient, or rather it would be much more convenient to solve the problem if we draw the velocity triangles properly. So, the first task should be to draw the velocity triangles and then we can calculate the parameters, those are asked in this problem. So, if we solve the problem, as I said that first it would be essential to draw the velocity triangles. So, let us now draw the velocity triangles. In fact, we have discussed this part in the context of the derivation of impulse turbine blading efficiency or diagram efficiency. So, if we consider this is the blade velocity u, I am writing here blade velocity u, sometimes it is also written or denoted by Vv, and if we complete the inlet velocity triangle first. So, that is the absolute velocity of steam coming out from the nozzle, which is making an angle alpha or alpha 1, that is the nozzle angle, and since the wheel is rotating, so the velocity of steam relative to the blade velocity is the relative velocity and we can draw this. So, this is W1. So, here C1 is the absolute velocity at the blade inlet, W1 is the relative velocity at the inlet, right. And since I have also discussed this part that blade velocity is calculated based on the mean diameter, and if you look at the problem statement, it is given that the mean diameter of the wheel is 100 centimeter. That means, we can now superpose the outlet velocity triangle on the common VB or common velocity blade velocity. So, now if we draw the outlet velocity triangle, then this is C2 and this is W2. So, say this is A, this is point B, this is point C and this point is D, this point. So, triangle ABC, that is the velocity triangle which is at the inlet of the blade, and triangle BCD, that is the velocity triangle at the exit of the blade, and we can see that this angle is beta 1, that is blade angle at the inlet, this angle is beta 2, that is blade angle at the outlet, and this angle is alpha 2, right. Most importantly, the component of absolute velocity in the axial direction, that is CA1, that is the flow velocity at the inlet. Similarly, component of absolute velocity in the axial direction, that is CA2, that is the flow velocity at the outlet, and we can clearly see that CA1 is not equal to CA2 from the velocity triangle, and since there is no pressure drop of the steam when it is passing through the blades or moving blades, the relative velocity at the exit of the blade is not equal to the relative velocity at the inlet of the blade, and that too we had seen that it is because of this roughness of the blade passage of blade surface, there is a reduction in the relative velocity, and that is why we could define blade velocity coefficient Kb or K. So, this is, we can see that CA1 is not equal to CA2 and this component is delta Ca, this is delta Ca. This component is responsible for the axial thrust that would be produced. Similarly, if we try to draw the component so this is W theta 2 and this is W theta 1, or we can write this is C theta 1 and this is C theta 2. So, that is C theta 1 is basically component of absolute velocity in the tangential direction, and c theta 2 is the component of absolute velocity in the tangential direction at the exit, and c theta 1 is the component of tangential velocity at the inlet. So, this delta c theta 2, so delta c theta equal to c theta 1 plus c theta 2. So, this is c theta 1 plus c theta 2, and delta C A equal to C A 1 minus C A 2. So, this delta C theta is responsible for the tangential thrust, and it is because of this thrust we are getting work output power, and delta C A that is responsible for the axial thrust, and that thrust should be consumed by the bearing. So, with this velocity triangles, in fact, today we will be solving a few numerical problems. We will be using this similar velocity diagram at least for the impulse turbine, and two important relations that I would like to now write from the velocity triangles that we have drawn. One is, if you look at that, this, as I said you, this delta c theta and delta C A, these two components are very important to calculate the tangential as well as axial thrust. So, we can see there are two ways by solving, there are two ways by which we can really solve the problem. One is through graphical representation, that is called graphically. So, basically if we can calculate the mean velocity, because mean velocity can be calculated because RPM is given, diameter is given, from there we can calculate. And if we now use a suitable scale to represent that mean velocity, and knowing the nozzle angle, we also can know what would be the absolute velocity. But today we shall try to solve the problems analytically just by using the trigonometric relations. So, what we can see that we can now calculate that mean velocity, that is very important quantity u, that would be equal to pi d n by 60. So, this d is dm if n is RPM. So, we can calculate mean velocity alpha 1 if it is given, then next we can calculate C 1. Now, two relations will be used today. One is, if we look at that what is delta c theta. Delta c theta is equal to w theta 1 plus w theta 2, that we can see from the geometry. This is as good as c theta 1 plus c theta 2. So, in other way, if we go to the next slide, we can write delta c theta equal to c theta 1 plus c theta 2, right, is equal to w theta 1 plus w theta 2 as well, right, that we will be using, because essentially you have to calculate delta c theta for the tangential thrust. Another thing, if we now look at the inlet velocity triangle ABC, we can now see that CA1 is equal to C1 sin alpha 1. So, we can write CA1, that is flow velocity at the inlet, that is the component of absolute velocity in the axial direction at the inlet, equal to C1 sin alpha 1. Again CA1 equal to, if we look at the velocity triangle, if we give name, this is AE. So, from triangle AEC we could write that AE equal to C1 sin alpha 1. Similarly, if we now look at the triangle AEB, that means AE, that is CA1 equal to, we can write that W1 by W1 sin beta 1, that we can write. So, these are very important to calculate the parameters that we will be using. So, now what is important, you know, that C1 sin alpha 1 minus u. So, if we consider C1 cos alpha C1 sin alpha 1 minus u, that means we can write that this CA1 equal to, so we can write now that W1 cos beta 1, this is W1 cos W1 sin beta 1, right. Now, we also can write another important relation, that from triangle ABC, C1 cos alpha 1 minus VB, that is from triangle ABC we can write C1 cos alpha 1. If we go to the so this is EC, triangle ABC, that is C1 cos alpha 1 minus VB, triangle ABC and triangle AEB. What we can write? C1 cos alpha 1 minus VB equal to this, that is EB, that is equal to W1 cos beta 1, right. So, C1 this equal to EC equal to C1 cos alpha 1 minus U or VB equal to EB. So, I can write U because we have used U. So, this is not VB, rather it is U. We have used U to denote the blade velocity U. So, that we can write, this indicates from the velocity triangles that EC minus BC. So, this is EC minus BC equal to EB, and also we can write that C1 W1 sin beta 1 W1 sin beta 1 equal to C1 sin alpha 1. So, C1 sin alpha 1, that is already we have written, equal to C1 equal to W1 sin beta 1. So, from these two relations we can write tan beta 1 equal to C1 sin alpha 1 divided by C1 cos alpha 1 minus U. So, this expression we will be using today to calculate beta many times. So, now let us go back to the problem statement. Already we have drawn the velocity triangles for the blades. Second thing, calculate the tangential, axial and resultant thrust. So, as I said you, if you would like to calculate tangential thrust, I am using F T, that equal to, as I said, tangential thrust is m dot S into delta C theta. So, this is mass flow rate of steam, right, and delta C theta, if we go back to the previous slide, I have already written. So, this is the expression of the delta C theta, to be precise, W theta 1 plus W theta 2, right. So, this is W theta 1 plus W theta 2. Now, if we go to the, so this is W theta 1 plus W theta 2, W theta 1 is equal to W1 cos beta 1 equal to W1 cos beta 1 plus W2 cos beta 2, W2 cos beta 2, right, that we can see from the velocity triangles. Now, if we again read the problem statement, so basically we know the blade velocity coefficient Kb equal to W2 by W1, and that is given, if we look at the problem statement again, it is given the ratio of relative velocity of steam at the blade outlet to that at the inlet is 0.86. What does it mean? That is W2 by W1 equal to 0.86, that is the blade velocity coefficient. So, you can understand, if we can somehow calculate W1 from the data given and using the blade velocity triangles, we will be able to calculate W2. Now, what is given? It is also given that ratio of blade velocity to steam velocity is 0.44, right. So, it is given. So, if we go here, it is given that blade velocity to steam velocity, right, u by C1, blade velocity to steam velocity. So, blade velocity u divided by C1, that is 0.44, right. So, already we have calculated u, and u equal to pi into 100 centimeter 2800 rpm divided by 60. So, that is the u, right, because mean diameter is given 100 centimeter. If we calculate, we will be getting the mean velocity, that is equal to 146.53 meter per second. I would suggest you to check the numerical value or numerical values, to be precise, for the problems that we will be solving today, for the to ascertain that I have calculated, I might have done some mistake while calculating these values, but you may check. So, this is the u. So, from these relations we will be getting C1 equal to u divided by 0.44, and we will be getting W u equal to, this would be equal to 0.44. So, there is a little mistake. So, this should be 157 meter per second. So, this is 157 meter per second. So, it should be 157 divided by 0.44 would be equal to 356.82 meter per second. So, this is C1. So, this is u, this is u, and this is C1. So, we could calculate the absolute velocity of steam at the exit of the nozzle, that is at the inlet of the blade, and also the blade velocity, right. Now, what we can do, we can use what would be the beta 1, because that is very important. So, now if we calculate, there are two ways. We will be using this expression to calculate beta 1, because already we have calculated C1, alpha 1 is equal to given, and already we have calculated u. So, using this relation, if we calculate beta 1, so basically if we write the expression tan beta 1 equal to C1 sin alpha 1 divided by C1 cos alpha 1 minus Vb, right. So, if we calculate alpha 1 equal to 20 degree, that is given, right. If we calculate, you will be getting the value of, and again I am writing Vb, I should write this is u, because I have used here u is the blade velocity, and u equal to, we have already calculated 157 meter per second, and beta 1, if we calculate, this is 0.6731, therefore, beta 1 equal to tan inverse 0.6731, and you will be getting 33.95 degree. So, you can check again the numerical value I am telling, but the procedure is correct. So, this is the beta 1. Now, calculating beta 1, and as I told you that beta 2 is given, if we go back to the problem statement, it is given that the blade outlet angle is 3 degree less than the blade inlet angle. So, that means from the problem statement, beta 2 equal to beta 1 minus 3 degree. So, it should be 30.95 degree, right. So, basically if we would like to calculate delta C theta, that is W theta 1 plus W theta 2, right, that already we have mentioned here, that is W 1 cos beta 1 plus W 2 cos beta 2. So, try to understand that W 1 cos beta 1 plus W 2 cos beta 1 minus 3 degree, right. What about W 1? W 1, if we now look at this expression that W 1 equal to C sin alpha 1 divided by sin beta 1, because we know alpha 1, we know C 1, we know beta 1. So, we can calculate W 1. So, we can write that is C 1 sin alpha 1 by sin beta 1 into cos beta 1 plus W 2 equal to kb into W 1 cos beta 1 minus 3 degree. So, why I am writing it? So, this is beta 1. See, in this expression everything is known, C 1 is known, beta 1 is known, beta 2 is also known, kb is known, then we can calculate what would be delta C theta. And if we can calculate delta C theta, then tangential thrust Ft will be equal to m dot s into delta C theta, that you can calculate. I am not calculating because this m dot s is given, that is equal to that given 10 kg per second. So, this is 10 kg per second. Similarly, we can calculate axial thrust F A, that equal to m dot s into delta C A, right. So, now how can we calculate delta C A? Delta C A equal to, so delta C A, if we look at the geometry, delta C A equal to C A 1 minus C A 2. See, what is C A 1? Because already we know beta 1 and already we know W 1. So, that is C A 1 by W 1 equal to sin beta 1, and beta 2 already you have calculated, we know W 2 from the blade velocity coefficient, blade friction coefficient, and then we can easily calculate from these velocity triangles. So, we can write this, that W 2 sin beta 2, this is W 1 sin beta 1 minus W 2 sin beta 2 equal to, therefore, delta C A equal to W 1 sin beta 1 minus kb into W 1 sin beta 2. So, again you can calculate easily what would be delta C A, because W 1 is known, beta 1 is known, kb is known and beta 2 is known. So, this is 33.95 degree, this is 30.95 degree, kb is given 0.86, and this W 1 already you have calculated, that is C 1 sin beta 1 by C 1 cos beta 1 by C 1 W 1 W 1 equal to C 1 sin alpha 1 by sin beta 1. So, this is alpha 1. So, this should be alpha 1 not beta 1, this should be alpha 1. Okay. So, sin alpha 1 by sin beta 1. So, you can calculate what would be axial thrust. Knowing or calculating these two quantities, we can calculate resultant thrust. Fr equal to under root Ft square plus Fs square. So, that would be resultant thrust. Nice. So, if we now move to the another part of this problem, that is power developed by the blades. So, let me tell you power developed by the blades. Now, I am coming to the power blades, that is P. So, let me tell you once again, you can easily calculate delta C and delta C theta because all quantities are known, right. Because this C 1 is 356.82 and alpha 1 20 and beta 1 33.95. So, you can easily calculate W 1. So, now what would be power developed, that is tangential thrust into velocity, of course blade velocity, right. We can write, we can divide this quantity by 1000 to write the quantity in kilowatt unit. So, tangential thrust is m dot delta C theta into U divided by 1000, the unit should be kilowatt. So, I try to understand, had we calculated tangential thrust correctly, we have already calculated blade velocity, we can easily calculate what would be the power developed by the blades. And finally, blading efficiency. See, let me tell you one thing. So, this is the power we are getting. Now, power developed by the blades at the cost of some input energy. So, this much amount of power developed by the blades at the cost of the input energy that is supplied to the blade. So, we can write it that this efficiency is defined by the ratio of rate of energy input to the blade and rate of work done, that is power on the blade. So, rate of work done on the blade, that is power developed by the blade to the rate of energy input to the blade. If we now try to simplify this quantity, that means you can understand that this should be m dot s delta C theta into U divided by half m dot s into C 1 square. So, basically kinetic energy of the jet, which is available at the inlet of the blade, and this is at the cost of this energy, this much amount of power is developed. So, that means we can write one step further, and we can write one step further here, and that is 2 delta C theta U divided by C 1 square. Now, can't you calculate this quantity, because already we have calculated delta C theta and we know blade velocity, and we have already calculated C1, that is absolute velocity of steam leaving the nozzle. So, we can calculate the blading efficiency. So, with this, next move to the another problem. This is the problem statement 2. It is given, let me read out the problem statement again first, and then we shall start solving the problem. In a single stage impulse turbine, it should be a single stage. There is a mistake in the problem statement itself. It should be in a single stage impulse turbine. The mean diameter of the wheel is 100 centimeter. Speed of rotation is 2800 rpm. The velocity of steam at the exit of the nozzle is 280 meter per second. So, C1 is given here. So, let us first again solve the problem. I mean, before solving the problem, let us first write the data given. So, it is given dm equal to 100 centimeter, alpha 1 equal to 25 degree. Try to recall the velocity triangles that we have drawn in the context of the previous problem. Now, dm equal to 100 centimeter, alpha 1 equal to 25 degree, and velocity of steam C1, that is 280 meter per second, right. The turbine blades are symmetrical, and due to friction in the blade, the relative velocity of steam at the blade outlet is 0.87 times the relative velocity of steam at the inlet. That means, we need, the problem statement is telling us to consider the blade velocity coefficient. So, basically it is given the blades are symmetrical. Blades are symmetrical. What does it mean? Normally blades are symmetrical. We have to, that this particular part I had mentioned, that if it is not provided, we have to assume that the blades are symmetrical for the impulse turbine, beta 1 equal to beta 2. Blades are fabricated from the same dies. So, basically the blades are geometrically similar. So, beta 1 equal to beta 2, and it is given that the relative velocity of steam at the blade outlet. So, relative velocity of the steam at the blade outlet is 0.87 times of the relative velocity at the inlet. That means, relative velocity at the blade exit is less than the blade relative velocity at the blade inlet. This is because of the friction. So, that means it is given that blade friction or blade velocity coefficient Kb equal to W2 by W1 equal to 0.87. So, all these data are given. We have to calculate the power developed when axial thrust on the blades is 150 Newton. So, what we can do? We can again draw the velocity triangles. This is C1, this is W1, this is alpha 1, this is C2, this is W2, this angle is beta 1, this angle is beta 2, and this is alpha 2. So, you know that this is W2 and this component is delta Ca. This is Ca2 and this is CA1, right. So, if we give name, this is A, this is B, this is C, and this point is D, and this is the relative velocity at the exit W2. Okay. Now, first we can calculate u, that is pi dm n by 60, and if we calculate, this is pi into 100 into 2800 divided by 100 into 60, because this is 60 and you will be getting 146.53 meter per second. So, this is the velocity, blade velocity, or so this is blade velocity. Okay. Now, let me tell you, as I had mentioned, we can use the relation tan beta 1 equal to C, C1 sin alpha 1 divided by C1 cos alpha 1 minus u, right. So, C1, that is given, C1 is given 280 meter per second. So, already C1 given. So, if we now calculate, so that is 280 into sin 25 divided by 280 cos 25 minus 146.53, and if we calculate beta 1 equal to, you will be getting 47.81 degree. I am telling once you, I am once again telling you that please check the numerical value, but the procedure is correct. So, this is the beta 1. Once we have calculated beta 1, then quickly we can calculate W1, because W1 equal to C1 sin alpha 1 divided by C1 sin alpha 1 divided by sin beta 1, right. So, the first step should be to calculate beta 1. Once we calculate beta 1, C1 is known, alpha 1 is known, we can calculate W1. So, that is 280 sin 25 divided by sin 47.81, and you will be getting the value, that is 159.7 meter per second. So, this is W1. So, see, as I told you that we also can solve the problem graphically, because if we can we have calculated u. So, if we use suitable scale, we can represent that u, and we know alpha, so we can calculate C1, but now we could calculate C1 is already given. So, we can calculate CA1 in its other quantities, but now we are trying to solve it analytically. So, W1 is this, we have calculated W1, then W2 equal to 0.87 times W1, that is given, right. So, W2 should be 0.87 times into 159.7, and that is equal to 138.95 meter per second, right. Question is, we have to calculate, if we go to the problem statement again, calculate the power developed when axial thrust on the blades is 150 Newton. That means, axial thrust Fa, that is m dot s into delta Ca. So, this is the axial thrust. So, this is equal to 150 Newton, that equal to m dot s into Ca1 minus Ca2, right. So, what is Ca1 minus Ca2? So, Ca1 equal to C1. So, we can calculate what would be m dot s, that is 150 divided by Ca1 minus Ca2. Now if we go back to the this geometry, we can see CA1 equal to C1 sin alpha 1. So, CA1 equal to C1 sin alpha 1, and what about CA2? CA2 equal to W2, CA2 equal to W2 sin beta 2. Right? It is given beta 1 equal to beta 2, right. So, what we can do, C1 is already given, alpha 1 is given, we can calculate CA1. What was not given directly is W2, but we could calculate W2, and beta 2 is equal to beta 1, right. So, basically we can calculate beta 2, because beta 2 equal to beta 1. So, this is 150 divided by C1 equal to C1 sin 25 minus W2 is equal to 138, that equal to 138 138.95, and CA2 equal, we could write CA2 equal to sin beta 2. So, sin beta 1 equal to beta 2, that is 47.81, and if we calculate, we will be getting 9.75 kg per second. So, you can check again. So, this is 9.75 kg per second. So, this is what we could calculate. Now, we have to calculate what would be the power developed, right, because that is what the quantity of interest for this particular problem. So, now power developed, we can calculate easily. Power developed by the blades equal to, we know tangential thrust m dot s into delta c theta into u divided by 1000 if we do, so that we can write the unit kilowatt. So, that is kilowatt, provided this delta c theta and u, that is meter per second, and ms is equal to kg per second. So, what we can write it, already in this expression already this is known, that is equal to 9.75 meter per second. This quantity is also known, u equal to 146.53 meter per second. So, we have to calculate delta c theta, that is the tangential thrust. So, now we can calculate tangential thrust if we can calculate, then we can do, or tangential thrust equal to m dot s into delta c theta. That means, this change in swirl velocity delta c theta, that would be equal to, let me tell you once again, this delta c theta can be calculated, if we go back to the previous problem, and if we look at the this part, that is c theta 1 plus c theta 2 or equal to w theta 1 plus w theta 2. So, this is up to you. Now, if we consider w theta 1 plus w theta 2 for this problem, that is w theta 1 plus w theta 2, this w theta 1 equal to w1 cos beta 1, and this is w2 cos beta 2. Let us verify whether we had written it correctly or not. So, w theta 1, that means if we write here So, this is W theta 2 and this is W theta 1. So, W theta 1 equal to this angle is beta 1. So, W 1 cos beta 1 and this is equal to W 2 cos beta 2, right. So, it is correct. So, what we can do, W 1 is already known, W 1 cos beta 1 and W 2 equal to 0.87 into W 1 into cos beta 1, because beta 2 equal to beta 1. So, we can write W 1 cos beta 1 into 1.87, right. So, see, already you have calculated beta 1 and already you have calculated W 1. So, that way it is coming 159.7 into cos beta 1 equal to 47.81 into 1.87, and if we calculate it and if we plug in the value of delta C theta in the expression of power developed here. So, we can get power developed will be equal to, you can check that it is coming 286.56 kilowatt. So, you can check it whether it is correct or not. So, this is the problem. At least you can understand, while solving these problems we can understand, or we can recapitulate the theoretical part that we have learned. And finally, the last problem that I will solve today is from another type of turbine, that is the impulse reaction turbine. So, if you try to recall, we had established the expression of the blading efficiency for both impulse and reaction turbine. Today, we have solved two problems from the impulse turbine. This problem is from the impulse reaction turbine. So, what is the problem statement? Let us quickly read out the problem statement. An impulse reaction turbine having degree of reaction equals to 0.5. We know that this is sometimes called only reaction turbine, only to distinguish this type of turbine from the impulse turbine, or it is also known as impulse reaction turbine. And degree of reaction, you know that is the enthalpy drop in the moving blades to the total enthalpy drop that we have discussed, and the turbine runs at 2800 rpm. The inlet blade angle of the moving blade and the exit angle of the fixed blade are 30 degree and 20 degree respectively. Mean diameter of the wheel is 0.6 meter and the steam condition is 1.5 bar with equality 0.95%. Of course, that is the steam quality at the inlet of the blade. Calculate the required height of the blade to pass 60 kg per second of steam and the power developed by the stage. So, let us quickly solve this problem. So, this is impulse reaction turbine, right. So, impulse reaction turbine as I said you that this type of turbine is also known as reaction turbine, because sometimes this type of turbine if we need to distinguish them or just to differentiate them from the impulse turbine, we call it reaction turbine. Otherwise, the impulse reaction is also a common name of this type of turbine. And degree of reaction are equal to half, and we know that degree of reaction is basically enthalpy drop in the moving blades to the total enthalpy drop. The difference is, the fundamental difference is, in a reaction turbine when steam passes through the blades or moving blades, pressure drops, and at the cost of the pressure drop, you know that the relative velocity is increased little, and steam turbine rotates because of both impulsive effect, that is change in momentum due to the change of direction of the jet, as well as the reaction force. That reaction force is impressed on the blades in the opposite direction. So, for R equal to half, that is this degree of reaction equal to enthalpy drop delta H moving blades divided by total enthalpy drop, that is delta H MB plus delta H fixed blades. Now, if R equal to half, then you can understand that means delta H moving blades equal to delta H fixed blades. So, this is for R equal to half, and for such a turbine, basically let me tell you, as I told you, that typically blades are symmetrical, because fabricating blade or blades of a turbine is not so easy. So, basically blades are fabricated from same dies, and beta 1 equal to beta 2 for the geometrical similarity. So, basically blades are similar, geometrically similar. Right. Otherwise, we have to use different dies for different blades. So, that would be again much more expensive. So, beta 1 equal to beta 2, and for R equal to half, C1 equal to W2, that is absolute velocity of steam from the fixed blade or nozzle is equal to relative velocity of steam from the exit of the moving blades. And if we know that we are using a common VB to superpose the velocity triangles. So, that means if we consider velocity triangles both at inlet and outlet of the blades, then we can see these two triangles are having a common side, that is VB. Beta 1 equal to beta 2, this C1 equal to W2, right. So, the blades are the triangles are symmetrical. So, basically if we try to draw the velocity triangles, triangles will be symmetrical. Let us first draw the velocity triangles and then we will discuss. So, if we draw the velocity triangles here, so this angle is alpha 1, this is beta 2, this is beta 1, this is C1, this is W1, this is W2, this is C2, and this is alpha 2. Okay. So, if this is triangle A, this is B, C and D. So, for R equal to half, triangles are symmetrical. Okay. So, that means triangle ABC equal to triangle BCD. Now, what we can write? We can write for R equal to half, that is C1 equal to W2, right, alpha 1 equal to beta 2, beta 1 equal to alpha 2 and C2 equal to W1. So, try to understand, we have a common base, common side BC, blades are symmetrical. So, triangles are symmetrical, and from if we consider these two triangles, we can write C 1 equal to W 2, alpha 1 equal to beta 2, and alpha 2 equal to beta 1, and C 2 equal to W 1. Now, question is what are the data given in this problem statement? It is given that we can easily calculate U. So, U equal to pi dm n by 60, and it is given 0.6 meter into 2800 divided by 60, and that equal to 87.92 meter per second. So, that is the mean velocity, and that is the mean velocity. So, this is U, blade mean velocity, and it is given that the inlet blade angle of the moving blade and exit angle of the fixed blade. So, basically it is given inlet blade angle of the moving blade. So, beta 1 equal to 30 equal to alpha 2, and it is given exit blade angle and exit angle of the fixed blade, that is nozzle. So, basically it is given beta 2 equal to alpha 1 equal to 20 degree. So, these are the data given. So, we need to calculate the power developed, and it is given. So, try to understand, we have to calculate the power developed. Let me write here. So, power developed by the blade is equal to P, that is equal to m dot delta C theta U divided by 1000, if you would like to write the unit in kilowatt. What about delta C theta? This delta C theta equal to C theta 1 plus C theta 2. If we look at the velocity triangles, see C theta 1, so this is C theta 1 and this is C theta 2. So, C theta 1 equal to C 1 cos alpha 1 plus C 2. So, we can write that this equal to C 1 cos alpha 1 plus C 2 cos alpha 2. So, this angle is alpha 2, right. So, if we write, or we can write that equal to W 1. So, basically that this is alpha 2, or this is as good as equal to W 1 cos beta 1 plus W 2 cos beta 2, that we have discussed in the context of the solution of the previous problem, that is equal to W theta 1 plus W theta 2, right. Now, we can easily calculate what would be the value, because let me tell you one thing, what it is given, because we know everything. So, what we know? We know alpha 1 equal to 20 degree, right. We know alpha 2 equal to 30 degree. So, if we can calculate C 1 or C 2, then we can calculate easily delta C theta. How can we calculate C 1 and C 2? So, basically, or C 1 and W 1. So, we can easily calculate if we look at the triangle ABC, and if we apply law of sines or sine law, then we can easily calculate what would be C1, because already we know U1. So, applying sine law, so applying sine law, we can write C1 divided by sine 180 minus beta 1 will be equal to W1 divided by sine alpha 1 equal to U divided by sine A. So, U divided by sine A, this angle equal to W1 divided by sine alpha 1 equal to C1 divided by sine 180 minus beta 1. That is clear. C1 divided by sine 180 minus beta 1. Now, from this what we can write? We can easily calculate what would be C1, that equal to, because we can compare the first one with the last one, that is U sine 1, what is beta 1? Beta 1 equal to 30 degree, right. So, sine 180 minus 30 divided by sine A, and angle A is 180 minus 150 plus 20 equal to 10 degree. You can check. So, this is, you will be getting, so this is equal to, so if I write it sine A, so that means we can write this is sine 10, this is sine 10, and you will be getting the value 253.15 meter per second. And similarly, we can get W1 equal to U sine alpha 1 equal to 20 degree, that is already given, divided by sine 10, and that would be equal to 173.16 meter per second. I am telling you once again to check the numerical values. So, C1 equal to and W1 equal to we have calculated, right. Now, we can calculate what would be this delta C theta next. So, delta C theta equal to C1 sin alpha 1, that we have already written, C1 cos alpha 1, C1 cos alpha 1 plus C2 cos alpha 2. Okay. So, C1 equal to C1 cos alpha 1 plus C2 would be equal to W1, and alpha 2 would be equal to alpha 2 beta 1, right. So, here you know C1 already you have calculated in the previous slide, that is 253.15 meter per second, W1 equal to C2 equal to 173.16 meter per second, alpha 1 equal to 20 degree, beta 1 equal to 30 degree. So, for all this data we can calculate this delta C theta, and it is coming as 387.84 meter per second. So, this is delta C theta. Now, we can calculate the power developed, right, provided. So, we have calculated delta C theta already, we know U, we can calculate power developed provided if we calculate m dot, mass flow rate. How can we calculate mass flow rate? So, what is the problem statement given? see it is given m dot equal to 60 kg per second, right. So, 60 kg per second, then we can easily calculate the power developed P equal to, so we can calculate the power developed P equal to, we can calculate what is mass flow rate, 387. So, we m dot delta C theta U divided by 1000 kilowatt, right. So, what is U? 1000, and it is given. So, you can calculate 60 kg per second, right, 60 kg per second. So, you can write this is 60 kg per second, delta C theta equal to 387.84, and U already we have calculated here, U equal to 87.92, right, 87.92. So, we can plug in the value 87.92 divided by 1000 kilowatt, that you can check also. And last part is that we have to calculate, if we need to really have flow of steam 60 kg per second at this rate, then what would be height of the blade. So, one important part is that if we go back to the previous slide, it is given that steam condition is 1.5 bar with quality 95%. So, from there we can calculate what is the specific volume of steam at this condition. So, I am writing here that specific volume of steam. So, specific volume of steam at the inlet, at blade inlet, V equal to Vf plus x Vfg, right. So, if we calculate Vf corresponding to that pressure 1.5 bar, that is 1.5 bar into 0.1 megapascal, you can we have discussed about this, that we need to take data from the steam table, and it would be, I am writing 0.001053 plus 0.95, it is given into 1.1594. So, this is the specific volume of the steam. Now, let me discuss here that steam will flow. So, I can write here at the last slide that so basically if we write here that flow rate of steam, so this m dot into specific volume equal to flow velocity into flow area. M dot into specific volume, that is the flow rate. So, we have already calculated m dot, that is given 60 into the specific volume, that just now we have calculated using the given condition of the steam, that is Vf plus x Vf, this V equal to Vf plus x Vfg, and if we calculate it, you will be getting the value 1.1024 meter cube per kg. Okay. So, this is 1.1024 equal to flow velocity, that is CA1 into flow area, that is pi into d into blade height h. So, now try to understand, in this expression we know d, we have to calculate this h, that is the blade height h, provided if we know CA1. What is CA1? CA1, that is the flow velocity, that equal to C1 sin alpha 1. If we go to the previous slide, so this is CA1, that equal to C1 sin alpha 1. So, I am writing here, that is C1 sin alpha 1. We can easily calculate, because we have already calculated C1, we have already calculated, the alpha 1 is given. So, if we plug in the value of CA1 over here, d, this should be dm to be precise, then we can calculate easily what would be h. So, you can check what would be the numerical value of h, that would be of the order of centimeter. So, to summarize today, we have solved a few numerical problems from steam turbine. We have covered both impulse as well as impulse reaction turbine, essentially to illustrate the concept that we have learned from the theoretical discussion. So, with this I stop here today, and we shall continue our discussion in the next class. Thank you.